Thank you. Good afternoon. I think tradition holds that my purpose for this session, the post-lunch slot, is to keep you awake. I will do my best. One of the things I'll use to keep you awake are some pretty pictures. This is part of a neural network. You may not be familiar with seeing it like this, but I'll show you some more as we go along. Graphcore is a small British company, 75 people at the moment, growing like a weed. And our purpose is to design silicon processors to support machine intelligence. So we're not neuromorphic, but we are very much focused on the intelligence problem. So machine intelligence, MI. I prefer MI to AI. I think once we get intelligence right, there'll be nothing artificial about it. It'll either be biological or machine, but it won't be artificial. We all know why we're here. This is a big deal. This is possibly the biggest deal humanity has ever gone through. 300 years ago, people invented steam engines. Before that, if you wanted work done, you had to use muscles, human muscle or animal muscle. And just as the people who invented steam engines 300 years ago could not conceive that you might jump into a jet-powered aeroplane and go off to some Caribbean island for holidays, we cannot conceive what is going to happen next. What we do know is that it's important. That's why we're all here. And we also know that it's going to completely change what we think of as computing. Software will change. My moot is that hardware will change, of course. I think you agree with me. But also the whole idea of programming will change. Instructing computers will give way to building computers with the capacity to learn and then training them. There may be no programmers, or there may be a combination of programmers and trainers. One thing is certain, and that is that we don't know what we want yet. So how do we build hardware for it? And how do we write software for it? And intelligence, of course, needs to be embodied in some sort of agent, whether it is moving about, or whether it exists just in cyberspace. And a canonical agent is just a sequence-to-sequence translator. At least that's as much as I can simplify it. It takes a sense of sensor input as a sequence, and it produces actor outputs as a sequence. Not with a one-to-one correlation, of course. We hope that it operates on a Bayesian basis. In other words, it makes best use of the evidence available to be a good intelligence. And it has two fundamental components. One is a knowledge model, a digest of all of its experience, and the other is an inference engine. And it uses the inference engine to improve the model and to decide what actor outputs to produce. So learning is inference, and so is what the current fashionable use for deployed inference is also inference. Everything is inference. And inference is optimization, stochastic optimization, because the data is noisy, the data is incomplete, the data is often imprecise, wrong. So stochastic optimization is what the machine must do on some sort of knowledge model. And let us not forget that there are two parts to intelligence. One is perfecting a model that exists. So when you were born, your brain was formed. It grew for some years thereafter. It adapted slightly for the rest of your life. But it was basically a fixed structure, and during your life you attempted to improve it on the basis of your experience. But on top of that, your brain has come from an evolutionary process that contributes massively to its intelligence. So the search for machine intelligence is not just a question of optimizing intelligent structures or models, it's also a question of discovering models. And from a compute point of view, it's quite likely that the discovery of good intelligence models is more expensive than the optimization of them. Knowledge models are very high-dimensional data. That we can agree on, whatever they are. And the natural way to represent very high-dimensional data is as a graph. Of course, if you have many dimensions, then the structure must, by necessity, be sparse, otherwise it would be spectacularly large. So sparse graphs are the fundamental data structure, and it makes sense to organize computation on that data structure in a distributed manner to use the same graph structure. Here's one of those pretty pictures. This is AlexNet. This is AlexNet blown up into about 1 million tensor subcomputations, and then laid out with a distance-based cost metric in 2 dimensions. It looks kind of organic, doesn't it? Which is interesting. For efficiency, when running on a machine, it's important that these structures can remain static. In other words, that we don't need to evolve the connections of the graph rapidly. We don't need to evolve the number of vertices any more than the number of neurons and the connection of the axons in your brain evolves as you have different experiences. That's important for mapping a massively parallel problem to a massively parallel machine, whatever it is. And the same is also true to a limited extent of the search for new structures. In many cases, it is possible to couch an evolutionary search as a computation on a static graph. And if we can do that, then it will help us to build efficient machines. So our comprehension of machine intelligence is nascent, but also our mechanization of intelligence is nascent. It is only 5 or 6 years ago that AlexNet woke everyone up to deep neural networks, as was observed earlier. And the amount of compute currently being used to do things like discover image classifiers is enormous. Certainly I've come across models which have cost $100,000 in electricity to run, just to run the program. $100,000 in electricity. So we've got to do something about it. We've got to build some better machines or reduce the search space, or I will attempt to produce better machines. And until we decide what it is we're trying to do with greater precision, I've suggested that these 4 points are what we should aim at. We need to exploit massive parallelism, because that's the only way of building massively powerful computers. We must be agnostic to model structure. We don't know enough yet. We don't know whether deep neural networks are it. We kind of like them because they're biologically inspired. But you only have to go back 5 years, and they weren't around to any significant degree. And it's still the case that many attempts to learn from data perform better with things like decision forests. So maybe neural networks aren't it. Maybe in 5 years there'll be something else. Maybe next year there'll be something else. So we've got to be agnostic to model structure. We've got to have a simple way of programming these things. The world has not yet been faced in anger with the problem of programming a massively parallel machine. Take debugging, for example. The standard GDB way of debugging a program that runs on the 4 ARM cores on your mobile phone is to open 4 debug windows on your screen. Noodle about with the code in one and see what happens in the others. Try doing that with 10 million of them. So how do we debug a parallel program with 10 million interacting subprograms? Not clear. So we need simple programming abstractions. And also, I don't believe structurally that there should be a difference, well, architecturally, that there should be a difference between machines for training and machines for inference, which is currently a sort of industrial theme that there will be such a difference. It's almost like building something, building a human that's capable of learning. You send it to school, you send it to college. As soon as it comes out of college, you turn off its learning function, because it's now fully trained, and you send it out to be deployed intelligence. That doesn't make any sense to me. I don't see any reason not to continue to learn. Here are my bets for what you could possibly build a machine based on today. And I say possibly, I have, obviously we have, which I'll show you in a moment. These are the things I think you can rely on today. They're not very rich as a set, and they say nothing about model structure, etc. We know we have huge parallelism. We believe that we can get away with very low precision arithmetic. The The dynamic range is still surprisingly large in many cases, so floating point, I would suggest. There are attempts to build integer-based machines, so far not very flexible. So small floating point numbers, that's almost inevitably adequate because of the stochastic nature of learning and the fact that we're building probability distributions from very noisy, inadequate data. There are some invariances that we can take from natural data, the data we're interested in. Things like speech, time sequence. There are characteristics of speech which it doesn't really matter when they occur, we just need to detect the characteristic. In images, we know that spatial invariance, for example, is important. If we're trying to detect a person's face, it shouldn't matter where the face is in the image sensor. So we can build machines, and of course, in the deep neural network framework, these invariances become convolution in space and recurrence in time. They're just invariances in space and time, respectively. So we can build machines to be more efficient with those. And also, probably we want our machines to be able to generate quite a lot of data. Quite a lot of noise. Noise is very useful. I don't think there are any massively parallel processors, or indeed less parallel processors, that have been designed with a mandate to generate a lot of noise. But I think this generation will have that mandate. And we have certainly built a machine specifically with the ability to generate an enormous amount of noise. So if your bag is noisy systems, then you may find this machine interesting. So important new workloads justify new architectures. I believe there will be new architectures. These are not neuromorphic. These are new architecture extensions of what we know about building von Neumann-style machines. And I think these machines will be designed specifically for computation on large graphs. They won't be CPUs, they won't be GPUs. I'm going to call them IPUs for intelligence processor. You can call them what you like. Now, silicon today, of course, as we know, I feel almost embarrassed saying this in an Intel building, but I have used some Intel examples here. These are big Xeons from the last 5 process generations to illustrate the point. Silicon is limited by power. We can scale the number of transistors per chip faster than we can scale the amount of compute per watt. Now, what that's the same as, so I've shown RAM density, logic transistor density on one pair of colored lines there, and cycles per joule, which is, if you like, compute per watt, heading in the same direction as the other densities, is clearly going up more slowly. What that means is, as we go forward in process generation, the amount of logic that you can power on your chip at full speed, at the speed the process is capable of, goes down. This is not news to anyone in silicon, of course. This has been the case for some time. And if you believe that when you buy an NVIDIA GPU today, that you're buying a box full of floating point units, and when you crank it up to max, they're all working, you're wrong. They're not. More than half the die is quiet. It has to be. Otherwise, it would burn too much power. And that story gets worse as we go forwards. So what do you do with all that dark space? 2 choices. You can either put stuff for other applications. That's currently what GPUs do. They have stuff for graphics that you don't use when you're doing AI. They have stuff for HPC that you don't use when you're using graphics. It's a reasonable way to build a chip. You sell it to multiple markets. But you need more and more markets as you go forward in process technology, so that's probably not going to continue. What else could you fill it with? The answer is memory. The obvious answer is memory. All future high-performance throughput silicon chips will be memory-dominated. And I would say my guiding mantra on this is that silicon efficiency now is nothing to do with maximizing the use of transistors. It is to do with maximizing the use of the available power. If you build a silicon processor, whatever the structure, and it uses all the power available all the time, then it's efficient. And in order to do that, you need to do various things. You need to distribute memory so that data values don't have very far to go every time you fetch them, and also so that you fetch them from small memory elements. which minimizes power. If you cannot store something that you need to retrieve locally, then consider recomputing it rather than storing it. Computation is becoming very, very much cheaper than storage. It is often the case that recomputation is cheaper. Communications, they're very expensive if they take the machine by surprise. And it has been historically the case that we build processor-to-processor communication structures that are asynchronous. So you always take the machine by surprise. You have people waiting. You have messages colliding. These are bad. These waste performance and they waste energy. So what we need to start doing, just as we do with compute, is we need to start compiling the communication. Now, in order for that to happen, the communication has to be deterministic, at least mesocronous. Asynchronous communication is bad news. You need synchronous communication to be power efficient. I'm going to let that sink into a neuromorphic audience for a moment, because I hear the opposite message frequently. And thirdly, you need to serialize communication with compute. I've been designing microprocessors for 35 years. Most of the time, I've been trying to get everything to work all at the same time. Now, it turns out that's power inefficient. It's actually more power efficient to throw all of your power at compute for a while, and then to throw all of your power at communication for a while, than it is to try and overlap them. I may have time to explain that. There's one further consideration in terms of building chips, and that is that complex microarchitectures in processors we know have a poor return. Pollock's rule says roughly square root number of transistors is what you get in terms of performance. It's not a physical law, but it has turned out to be roughly true. So if you're trying to build a maximum throughput performance machine, you need lots of small processors, not a few big, complicated ones. So you need something like this, a pure distributed machine in which you have processor tiles that have some compute resource and some memory resource, and they communicate with each other through a stateless interconnect. Nothing shared, so that you can scale it to thousands or millions of processors. You can still use threads, but don't use them to hide latencies over the whole chip or to external memory. Use them just to hide latencies locally to the processor so that you can make timing deterministic, so that you can make as much as possible compilable, so that you have as little as possible in terms of hardware to deal with taking the machine by surprise. Here's a quantification, roughly, for those of you that are not familiar with silicon, of what you can get in 16 nanometers. In about 1/4 of a square millimeter, you can build something like a 200 gigaflop processor now. A flop here is a 16-bit multiply IEEE, 32-bit IEEE accumulation. So about 100 billion max per second in 1/4 of a square millimeter. You can't fill the die with those because you haven't got enough power. In about 1/3 of a square millimeter, you can have about 256 kilobytes of RAM. If you split it into 16 pieces, then you can access it roughly as fast as a processor might go. And if you access, say, a reasonable amount for that processor, then that adds about another 25%. So its effective power density is rather lower than the processor, which is why if you build chips that have a smaller fraction of processor logic and a larger fraction of memory, then you can maximize the power available. And that is our new definition of silicon efficiency. So here are the two schemes. On the left is what we do today. Big GPU sat on a silicon interposer with some HBM DRAMs around it. Only part of the GPU die can be powered because it's full of logic. All memory is in a separate technology. It gives you great memory density. So you get 16 gigabytes today, 32 in the future. And you can access that memory at about 900 gigabytes per second, state of the art today. On the right is what you could do, is what we do. Same power, same amount of powered logic. So same amount of performance, roughly speaking. Much less memory, because it's all local. It's distributed all over these two chips. You have two big die instead of one big die and some DRAMs. So each of the die has less power. It's about half the power. And I've just chosen 240 watts because that's roughly what you can spend on a PCI card once you've taken the power supply chips off. So you've got less memory, but it's much more local, so therefore less power per access. It's energy per access. And you've got massive access bandwidth, about 100 times as much, 90 terabytes per second. So if you can work out how to write software to make use of that smaller memory at much higher bandwidth, then that's a good deal. Now we need to expose, in order to fill a machine like this, an enormous amount of parallelism in our programs. I'll show you shortly. We put down thousands of these processors on a chip. And in order to make them load balanced so that I can predictably schedule things, ideally I'd like a list of work for each little processor to do. So say 1,000 work items per processor during the run of my program. And I can tell you, our customers today would like to join together 1,000 of these chips in order to make their neural network search run faster, 1,000 of them. So ideally, you'd like a program to expose parallelism of order 1 billion. Anyone know how to write such a program? I don't. That's something we must learn. Obviously, it's a direction that the neural network frameworks are trying to pursue. That's a beginning, though, I think. So we have built this chip. We call it Colossus, in honor of the designer of the first electronic computer. I'm looking around for people who disagree with that statement. Discuss afterwards. Tommy Flowers. It is all new, so there are no ARM cores in here or anything like that. This is a ground-up, bare silicon build. This is about 25 billion transistors. This is as big a chip as you can make. It's reticle-sized, 16 nanometer. And it's built specifically for this job of accelerating intelligence, by which I mean the optimization of existing models and the discovery of new models. It is mostly memory for reasons I've told you. So the operating model here is that your machine intelligence model lives entirely on this chip. You never go off to external DRAM to fetch any information. The model lives on the chip. It's designed to be clustered. So you can bolt together a sea of these things and they just act like a bigger one as far as possible. We can't actually sustain as much bandwidth between chips as we can on the chip, so it doesn't quite work like that, but we do the best we can. It operates under a parallel processing paradigm called bulk synchronous parallel. I may have time to describe that shortly. I may not. And it's designed to be programmed. It has its own native graph level abstraction, like a class library for graphs in C++, if you like, which we call Poplar. And you can program it closest to the machine in that framework. Or we also write APIs in that framework to allow you to program it in things like PyTorch or TensorFlow, which are the current fashions. What we do is we put 2 of these on a PCI card. So this is a 300-watt card, just like the diagram I showed you earlier. There are 2,432 little processors. Each can run about 100 gigaflops. You may not have quite enough power for that. We're still characterizing that. But certainly in aggregate, you have more than 200 teraflops of performance on one PCI card from this. And as discussed earlier, you have some tens of terabytes per second of memory access to local memory, and you have about 8 terabytes per second of processor-to-processor communication on each chip. Made by TSMC. Processors communicate with each other using this. 3 minutes. Time me. Using a paradigm known as bulk synchronous parallel. In this paradigm, if you're not familiar with it, you alternate between 2 phases. A phase of compute, in which Each processor computes just on data which is in its local memory. And then a phase of communication, in which data is exchanged between memories, but nobody computes on their data. And there is one synchronization each time you go around that loop. And the program iterates, going compute, exchange, compute, exchange. The compute stage lasts, or phase lasts for as long as it needs to. The exchange phase lasts for as long as it needs to. But they don't overlap. Actually, as you can see in this diagram, each of these vertical bars is supposed to be one processor. So there are just 6 here on each chip. In practice, we have 1,200 or so. You can see that actually there is some overlap allowed between the exchange phase and the compute phase. But that's it. So in order to make a machine like this, you have to be very good at load balancing, because each processor needs roughly the same amount of time to be used. You also have to have low-cost synchronization. This is something we can do today in silicon big time. Now, why does that make sense? Well, consider you're trying to design a microprocessor. You've got a certain power budget. Your mission is to use all the power all the time. Traditionally, you would have overlapped communication and compute. And so you would have had to budget a certain amount of power for compute, a certain amount of power for communication. Now, if your application didn't have that ratio, then what happens is that you use less than the full amount of power. Your program still takes the same amount of time because it's limited by one or the other. If you instead serialize them, which is what BSP does, then instead of your program running at lower power, it still runs at full power, but it takes less time. And that's what we want. We want maximum throughput. So this is why I say serializing communications and computing is actually more efficient in a power-limited world than overlapping them. The other nice thing about bulk synchronous parallel is it is the only, to my knowledge, way of constructing massively parallel programs which are completely hazard-free by construction. You can't write a program in this paradigm which has a live lock or a deadlock or a race, whereas in CSP or the actor model or anything else you might come up with, you can. I have. This is an actual trace that shows the alternation between exchange and communication, and compute. And those thin purple lines are the synchronization events. This is actually for a ResNet neural network, and this is just on one processor tile. That's a kind of folded. Consider that as being, it looks like a DNA thing, doesn't it? But it's one long line which I've chopped into pieces and folded up to fit on the page. And this is actually, so on each row of that, you have your 2,400 tiles arranged vertically. And you can see sort of optically there how much time roughly we get to spend doing compute, how much is spent doing exchange. And the light blue stuff is time that's lost. That's your inefficiency. And
how is the synchronization works? Because I see it's very short time.
Speaking of very short time, that's the end of my talk. This is ta-da!
So now it's a
this is ResNet 50, by the way, layer by layer. ResNet 50 has 50 layers, but many of them are identical. So if you're actually running a program, it's as if you've got a loop running around the same stuff sometimes. And what's lit up is the part of the graph that is active for that layer. It looks like a brain scan. It's marvelous.
So how do you do the synchronization in a way that is not hard on the system? Because I can see how you get from the parallel computation, you can do asynchronicity inside, so I can see how things will be very fast. But the synchronicity, how do you do it without upsetting the system and taking too much time?
I'm not sure what you mean by upsetting the system. The important thing is to be able to compile patterns of communication. Now, obviously, the actual communication you may need in the running of a program is data dependent, just as the compute you need is data dependent. But just as we compile what are called basic blocks, atomic units of compute, which are dynamically selected in conventional computing, we need to do the same with communication. You need to have communication sub-patterns which can be compiled onto a deterministic machine, and then those are dynamically selected. Now, they don't actually have to be synchronous, but you have to avoid taking the machine by surprise when unnecessary. So what they really need to be is mesocronous. In other words, things have to happen in the right order, because then you can arrange for a machine to be quite efficient. The synchronization, that's what's required to make sure that everyone knows what time of day it is throughout the runtime of the whole program. A SIMD machine effectively operates a clock on a per instruction basis. Everyone has to be aligned on every instruction. On a BSP machine, everyone just has to be aligned on the basic block of communication basis, which is typically, I don't know, 10 or 100 instructions. It could be thousands. But the synchronization on today's silicon on a chip, and also within a small cluster of chips, is actually super cheap. It wasn't when BSP was invented in 1990 by Leslie Valiant and Bill McColl. It was very expensive then, but not anymore.
Yes. Does Colossus do learning on chip? What kind? Supervised, unsupervised? Do you use FPUs for that? Just could you comment?
Colossus is a general purpose parallel processor that you can program in C++. So it'll do whatever you program it to do. Each of those little programmable tiles has 6 threads, each of which executes one vertex of a graph. So your compute is captured as a graph in which vertices have subprograms and also have local state. And they communicate by sending each other messages.
So does it contain a floating point unit inside each tile?
Each tile, yes, many of them.
Okay.
Many of them. It's a general purpose parallel processor, so it makes no assumption about what the model is or what the learning algorithm is or what the inference algorithms are.
Let's thank Simon again.